Right now, as you watch this video, every atom in your body is suspended in what might be a cosmic lie. The electrons orbiting your nuclei, the quarks binding together inside protons, the very forces holding reality together, all of it exists because of something called the Higgs field, an invisible ocean of energy that permeates every cubic centimeter of space. And here's what keeps physicists awake at night. We might be living in what's called a false vacuum, a universe that only appears stable, like a ball balanced on a hill, waiting for the slightest nudge to send it rolling into oblivion. If that's true, then somewhere in the cosmos right now, a bubble of true vacuum could be forming, expanding outward at the speed of light, rewriting the laws of physics as it goes. You wouldn't see it coming. You wouldn't feel it. One moment you'd exist, and the next, nothing. Not death, not darkness, just the complete erasure of the possibility of existence itself. This isn't science fiction. This is a serious prediction that emerges from our best understanding of quantum field theory and particle physics. In 2012, when scientists at CERN's Large Hadron Collider finally confirmed the existence of the Higgs boson, they measured its mass at approximately 125 billion electron volts. That number should have been cause for pure celebration, and it was, earning Peter Higgs and Francois Englert the Nobel Prize in 2013. But it also triggered a quiet alarm among theoretical physicists, because that particular mass, combined with the mass of the top quark, places our universe in a deeply unsettling region of possibility. According to calculations published by physicists Joseph Liken and Maria Spyropoulou, our universe appears to be metastable, balanced on the edge between stability and catastrophic collapse. To understand what this means, imagine you're standing in a valley surrounded by mountains. The valley floor feels solid beneath your feet. You can build a house here, plant a garden, live your entire life in apparent safety. But now imagine that this valley isn't actually the lowest point in the landscape. Somewhere beyond those mountains lies an even deeper valley, one you can't see from where you stand. Your valley is comfortable, but it's not the true ground state of the terrain. You're living in what geologists might call a local minimum. Stable for now, but not fundamentally stable. One good earthquake, one shift in the underlying geology, and the ground beneath your feet could give way, sending everything tumbling toward that deeper, truer valley. This is precisely the situation our universe might be in. The Higgs field, the field that gives particles their mass, that makes matter possible, currently sits at a certain energy value throughout all of space. We call this the vacuum state, though it's anything but empty. It's more like the baseline hum of reality, the 0 point from which everything else is measured. But quantum field theory suggests this might not be the lowest possible energy state. There might be another configuration, another valley, where the Higgs field has less energy. We call our current state the quote 1, and that hypothetical lower state the quote 2. And the difference between them isn't academic, it's existential. Here's why this matters in the most visceral way possible. In 1977, physicists Sidney Coleman and Frank DeLucia published a paper that would haunt cosmology for decades. They showed mathematically how a universe in a false vacuum state could transition to a true vacuum through a process called quantum tunneling. Picture it this way. Remember that ball balanced on a hill? In classical physics, it needs enough energy to roll over the top before it can fall down the other side. But in quantum mechanics, there's a probability, however small, that the ball can simply tunnel through the hill, appearing spontaneously on the other side without ever having climbed over the top. This is not metaphor. This is how quantum particles actually behave, confirmed in laboratories thousands of times. Now scale that up to the entire universe. Somewhere, in some random point in space, quantum fluctuations could cause a tiny bubble of true vacuum to spontaneously form. Maybe it's happening right now, 13 billion light-years away. Maybe it happened a billion years ago, and the bubble is already halfway here. Inside that bubble, the Higgs field would have a different value. And because the Higgs field determines particle masses, and particle masses determine how forces work, and forces determine chemistry, and chemistry determines everything from atoms to stars to consciousness, inside that bubble, the laws of physics would be completely different. The bubble wall would expand outward at exactly the speed of light. Not almost the speed of light, exactly the speed of light. Because the transition releases energy, and that energy drives the expansion at the maximum possible speed allowed by relativity. This means you could never see it coming. Light from the approaching bubble wall would arrive at exactly the same instant as the wall itself. There would be no warning, no time to prepare, no final moments to contemplate your existence. The bubble would simply arrive, and in less time than it takes for a single thought to form, every atom in your body would be torn apart and reassembled according to new rules. Rules that almost certainly wouldn't permit the existence of atoms as we know them, let alone molecules, cells, or conscious beings. But here's what makes this scenario particularly haunting. The bubble wouldn't just destroy matter. It would rewrite the past. According to quantum field theory, the true vacuum state has lower energy than our false vacuum. When the transition occurs, that energy difference has to go somewhere. It gets released as a violent expansion of the bubble wall, but it also fundamentally alters the structure of space-time itself. Some calculations suggest that the interior of a true vacuum bubble might not even contain time as we understand it. The very concept of, quote, 3 and, quote, 4 might cease to have meaning. You wouldn't die and leave behind a corpse, or even atoms, or even the memory of atoms. You would be erased from the possibility space of the universe, as if you had never existed at all. Joseph Liken, a theoretical physicist at Fermilab, put it this way in a lecture in 2013. If you use all the physics that we know now and you do this straightforward calculation, it's bad news. It may be that the universe we live in is inherently unstable, and at some point, billions of years from now, it's all going to get wiped out. But then he added something even more unsettling. Or it could happen tomorrow. The probability is extraordinarily low. So low that you shouldn't lose sleep over it tonight. But it's not zero. And that non-zero probability has been sitting there, ticking away, for every second of the 13.8 billion years since the Big Bang. Think about what this means for the nature of existence itself. We're used to thinking about threats we can see coming. Asteroids we can track, climate changes we can measure, even the eventual heat death of the universe trillions of years in the future. Those are dangers that exist within the framework of physical law. But vacuum decay is different. It's not a thing that happens within the universe. It's the universe changing its mind about what it wants to be. It's reality itself deciding to reboot with a different operating system, one that doesn't include a compatibility mode for anything that came before. And yet, here we are. You're still reading these words. Your heart is still beating. The electrons in your neurons are still firing according to the same electromagnetic laws they've followed since the first atoms formed in the cooling plasma of the early universe. Every second that passes is another second that the false vacuum, if that's what we're living in, has remained stable. Every breath you take is a small miracle of cosmic patience, the universe declining once again to exercise its option to delete everything. The strangest part? We might never know for certain whether we're in a false vacuum or a true one. The calculations depend on precise measurements of fundamental constants, the mass of the Higgs boson, the mass of the top quark, the strength of the strong nuclear force. As of 2022, our measurements place us right on the boundary between stability and metastability. A slight adjustment in any of these values, a small correction to our measurements, could tip the calculation one way or the other. We're living in a state of quantum uncertainty about the stability of existence itself. Some physicists find this terrifying. Others find it strangely liberating. If the universe could end at any moment through no fault of our own, through no action we could possibly take or prevent, then in a sense, we're freed from a certain kind of cosmic responsibility. We didn't break the universe. We can't fix it. We're just here, riding the wave of an improbable stability, making the most of whatever time the false vacuum decides to give us. But let's dig deeper into the physics, because the details make this even more fascinating and strange. The Higgs field isn't like other fields you might be familiar with. It's a scalar field, meaning it has a value at every point in space, but no direction. You can think of it like temperature. Every location has a temperature value, but temperature doesn't point anywhere. The Higgs field's value determines how strongly it interacts with different particles, and that interaction is what we experience as mass. Particles that interact strongly with the Higgs field are heavy. Particles that barely interact with it are light. Photons don't interact with it at all, which is why light has no mass and can travel at the cosmic speed limit. Now, in quantum field theory, every field has what's called a potential energy curve. This is a mathematical description of how much energy the field has at different values. For a stable field, this curve looks like a simple bowl, one minimum point at the bottom, and the field naturally settles there because that's the lowest energy state. But for some fields, the potential energy curve is more complicated. It might have multiple valleys, multiple local minima. The field could settle into one valley and stay there for a very long time, even if there's a deeper valley somewhere else on the curve. The Higgs field appears to have exactly this kind of complicated potential. Our current vacuum state, the value of the Higgs field throughout all of space, sits in one valley. But calculations based on the standard model of particle physics suggest there might be another valley, much deeper, at a different field value. The barrier between these two valleys is enormous, which is why we haven't spontaneously tunneled to the true vacuum already. But quote 7 in quantum mechanics doesn't mean impossible. It just means extremely improbable per unit time per unit volume. Here's where the numbers get both reassuring and disturbing. Physicists can calculate the approximate rate at which quantum tunneling events should occur for a given barrier height. For the Higgs field, with the measurements we have, the probability of a true vacuum bubble forming in any given cubic meter of space in any given second is roughly 10 to the negative power of 100. That's a decimal point followed by 99 zeros and then a 1. It's a number so small it barely deserves to be called a probability. For comparison, the probability of every air molecule in the room you're in spontaneously moving to one corner, leaving you in a vacuum, is vastly higher than that. But here's the catch. The universe is big. Really big. The observable universe contains about 10 to the power of 80 atoms. That's already a huge number, but it's nothing compared to the total volume of space. If the universe is infinite, as many cosmologists suspect, then there are infinite cubic meters of space where this tunneling event could occur. And if you have infinite opportunities for something to happen, even an infinitesimally small probability becomes a certainty. Not in any given moment, but eventually, somewhere. Even if the universe isn't infinite, it's still incomprehensibly vast. The observable universe has a radius of about 46 billion light-years, but that's just the part we can see. The actual universe is almost certainly much larger, possibly thousands or millions of times larger than the observable portion. Every cubic meter of all that space is rolling the dice every second, testing whether this will be the moment when quantum fluctuation creates a bubble of true vacuum. So far, for 13.8 billion years, the answer has been no. But the dice keep rolling. And if it happens, the bubble expands at light speed, which means it covers roughly 300,000 kilometers every second. In 1 year, it would expand across about 9 trillion kilometers, roughly 1 light-year. In a million years, a million light-years. The Milky Way galaxy is about 100,000 light-years across, so a bubble forming at the galactic center would consume the entire galaxy in 100,000 years. The Andromeda galaxy, our nearest large neighbor, is about 2.5 million light-years away. If a bubble formed there today, it would reach us in 2.5 million years. A blink of an eye in cosmic time, but an eternity in human terms. But what if the bubble formed closer? What if it formed in our own galaxy, say 10,000 light-years away? Then we'd have 10,000 years before the wall of annihilation reached us. Would we see it coming? Could we detect it? This is where the physics gets truly strange. The bubble wall itself moves at light speed, so we couldn't see it directly. But the interior of the bubble would have different physics, and that might produce observable effects. Stars inside the bubble might shine differently, or not at all. Galaxies might distort or vanish. We might see a growing sphere of darkness, expanding toward us at an appreciable fraction of light speed. Not the bubble itself, but the shadow it casts on the cosmos. Some physicists have speculated about whether an advanced civilization could detect an approaching vacuum decay bubble and do something about it. The answer, unfortunately, is almost certainly no. You can't outrun something moving at the speed of light, and you can't shield yourself from it because it's not a thing moving through space. It's space itself, changing its fundamental properties. It would be like trying to protect yourself from a change in the laws of mathematics. If 2 plus 2 suddenly equaled 5, no amount of armor would help you. But could we prevent it from forming in the first place? This question has led to some fascinating and disturbing speculation. In the 1980s, physicists Sidney Coleman and Frank DeLucia, along with others, explored whether high-energy events might trigger vacuum decay. If we're living in a metastable false vacuum, then concentrating enough energy in a small enough region might give the Higgs field the kick it needs to tunnel through to the true vacuum. This raised concerns about particle accelerators. Could the Large Hadron Collider, smashing protons together at energies of 13 trillion electron volts, accidentally trigger the end of the universe? The answer, thankfully, is no, but the reasoning is interesting. Cosmic rays, high-energy particles from space, routinely hit Earth's atmosphere with energies far higher than anything we can produce in accelerators. Some cosmic rays have energies exceeding 10 to the power of 20 electron volts, millions of times higher than the LHC. These collisions have been happening for billions of years, all over the universe, and we're still here. If such collisions could trigger vacuum decay, it would have happened long ago. The fact that we exist is proof that our particle accelerators are safe, at least from this particular existential threat. Still, there's something deeply unsettling about the idea that the universe is held together by nothing more than probability and patience. We're used to thinking of physical laws as eternal and unchanging, the bedrock upon which everything else is built. But quantum field theory suggests that even the laws themselves might be contingent, temporary, subject to change without notice. The speed of light, the charge of the electron, the strength of gravity, all of these might be nothing more than local bylaws, rules that happen to apply in our particular cosmic neighborhood, but could be revised at any moment. What would the true vacuum be like? We can't know for certain, but we can make educated guesses based on the physics. If the Higgs field dropped to a lower value, particles would have different masses. Electrons might become heavier or lighter. Quarks might not bind together to form protons and neutrons. The electromagnetic force might be stronger or weaker. In most scenarios, atoms as we know them couldn't exist. Chemistry would be impossible. Stars couldn't form, or if they did, they'd burn out in seconds or never ignite at all. The true vacuum would almost certainly be a sterile place, devoid of complexity, structure, or life. But here's a strange thought. Maybe the true vacuum would give rise to entirely different forms of complexity, structures and patterns we can't even imagine, because they'd be based on physics so alien to our experience. Maybe there would be something like matter, something like energy, something like consciousness, but built from completely different building blocks, following completely different rules. We tend to assume that our physics is the only physics capable of producing interesting phenomena, but that's probably just parochial thinking. The true vacuum might be just as rich and strange as our false vacuum, just in ways we literally cannot conceive. Or maybe not. Maybe the true vacuum is exactly what the equations suggest, a cold, empty, structureless void where nothing happens and nothing can happen. A universe that has finally reached its true ground state, with no energy left to drive change, no gradients to power complexity, no possibility of anything resembling life or thought or meaning. The ultimate heat death, not in the distant future but right now, everywhere at once, as soon as the bubble wall passes through. There's a photograph that hangs in the office of every quantum field theorist who studies vacuum stability. It's not a picture of an equation or a particle collision. It's an image of empty space, literally just darkness, taken by the Hubble Space Telescope when astronomers pointed it at a patch of sky that appeared to contain nothing at all. They left the shutter open for 11 days, collecting every photon that wandered into the lens from that supposedly empty region. When they developed the image, they found not emptiness, but thousands of galaxies, each containing hundreds of billions of stars, stretching back to within a billion years of the Big Bang itself. The photograph is called the Hubble Deep Field, and it revolutionized our understanding of cosmic abundance. But for vacuum decay theorists, it represents something else entirely: a map of targets. Every point of light in that image is a place where the false vacuum has remained stable for billions of years. Every galaxy is a monument to improbability, a structure that shouldn't exist if the universe were eager to transition to its true ground state. Let's talk about what we mean when we say vacuum, because the word itself is misleading. In everyday language, a vacuum is empty space, a region devoid of matter, like the inside of a vacuum-sealed jar or the space between stars. But in quantum field theory, the vacuum is anything but empty. It's the lowest energy state of all quantum fields, the baseline hum from which everything else emerges. Even in the deepest void of intergalactic space, far from any matter or radiation, quantum fields are still there, still vibrating, still fluctuating according to the uncertainty principle. These fluctuations aren't just theoretical abstractions, they have measurable effects. They create a phenomenon called the Casimir effect, where two metal plates placed very close together in a vacuum will experience an attractive force because the quantum fluctuations between the plates are restricted compared to the fluctuations outside. This has been measured in laboratories with exquisite precision. The vacuum, in other words, is an active participant in physical reality, not a passive backdrop. Now imagine that this active, fluctuating vacuum is sitting in the wrong energy state. Not dramatically wrong. The difference between the false vacuum and the true vacuum might be incredibly small in absolute terms, perhaps just a fraction of a percent of the total energy density. But in a universe where energy and mass are equivalent, where E equals mc squared, even a small difference in energy density translates to enormous consequences when multiplied across all of space. The energy difference between our false vacuum and the hypothetical true vacuum, integrated over the volume of the observable universe, would be roughly equivalent to the mass energy of all the stars in 1 trillion galaxies. That's how much energy is potentially locked up in the metastability of the Higgs field, waiting to be released if the transition ever occurs. This brings us to one of the most profound questions in modern cosmology. Why hasn't it happened already? If the false vacuum is unstable, if quantum tunneling is constantly trying to create bubbles of true vacuum, why has the universe survived for 13.8 billion years? The answer lies in the mathematics of quantum tunneling and the concept of a decay rate. When physicists calculate the probability of vacuum decay, they're not calculating the probability that it will happen. They're calculating the probability per unit time, per unit volume. Think of it like radioactive decay. A single uranium atom has a certain half-life, a characteristic time over which it has a 50% chance of decaying. But that doesn't mean all uranium atoms decay at once. Some decay early, some decay late, and the overall population decays exponentially over time. Vacuum decay works similarly, except instead of atoms, we're talking about regions of space, and instead of a half-life measured in millions of years, we're talking about timescales that dwarf the current age of the universe by factors of 10 to the power of hundreds. The calculations, performed by physicists like Alexander Kusenko and refined over decades, suggest that the expected time for a vacuum decay bubble to form somewhere in the observable universe is roughly 10 to the power of 100 years. That's a 1 followed by 100 zeros. For context, the current age of the universe is about 10 to the power of 10 years, 13.8 billion. The expected lifetime of the last stars in the universe, the tiny red dwarfs that will burn for trillions of years, is about 10 to the power of 14 years. The time it would take for every black hole in the universe to evaporate through Hawking radiation is about 10 to the power of 100 years, the same timescale as vacuum decay. In other words, if these calculations are correct, the universe is expected to survive in its current form until long after every star has died, every black hole has evaporated, and the cosmos has cooled to within a whisper of absolute zero. Only then, in the unimaginable depths of time, might a bubble of true vacuum finally form. But here's the unsettling part. These are expected values, averages over infinite trials. Probability doesn't care about expectations. A coin with a 50% chance of landing heads could land tails 100 times in a row. It's unlikely, but it's possible. Similarly, a vacuum decay event with an expected waiting time of 10 to the power of 100 years could happen tomorrow. Or it could have happened yesterday, 13 billion light-years away, and the bubble wall could be racing toward us right now, scheduled to arrive in 13 billion years, long after our sun has died, but long before the universe reaches its expected decay time. We have no way of knowing. The universe doesn't send out advance warnings when it decides to rewrite its own source code. This uncertainty has led some physicists to explore whether there might be mechanisms that stabilize the false vacuum, factors that make the transition less likely than the naive calculations suggest. One possibility involves the expansion of the universe itself. We know from observations of distant supernovae and the cosmic microwave background that the universe is not just expanding, but accelerating, driven by something called dark energy. This acceleration stretches space itself, pulling galaxies apart, diluting the density of matter and energy. But it also affects vacuum decay. When space is expanding rapidly, it becomes harder for a vacuum decay bubble to form and grow. The expansion fights against the bubble's tendency to expand, creating a kind of cosmic friction. Some calculations suggest that in a rapidly accelerating universe like ours, vacuum decay might be suppressed entirely. The bubbles could form but fail to grow, collapsing back into the false vacuum before they can reach catastrophic size. This idea, explored by physicists like Andrei Linde and Vitaly Vanchurin, offers a strange kind of comfort. Maybe we're living in a universe that's naturally protected against its own instability, where the very expansion that will eventually tear galaxies apart is also the thing keeping us safe from vacuum decay. But the comfort is limited. The calculations depend on the exact value of dark energy, which we don't know with perfect precision. And even if expansion does suppress vacuum decay in our current epoch, it might not have done so in the early universe, when expansion was slower, or in the far future, when the dynamics of dark energy might change. We're still rolling the dice, just with slightly better odds than we thought. Let's zoom out and consider the cosmic implications. If vacuum decay is possible, it's not just a threat to our universe, it's a filter, a selection mechanism that shapes which universes can exist and which cannot. This connects to an idea called the anthropic principle, which observes that we can only find ourselves in a universe capable of supporting observers like us. If most possible configurations of the Higgs field lead to rapid vacuum decay, then most universes would self-destruct long before stars could form, planets could cool, or life could emerge. The fact that we exist to ask these questions means we must be living in one of the rare universes where the vacuum is stable enough, for long enough, to permit the emergence of complexity and consciousness. But this raises a deeper question. Are we just lucky? Or is there something special about our vacuum state? Some physicists, including Steven Weinberg and Leonard Susskind, have argued that we might be living in a multiverse, a vast ensemble of universes, each with different values of fundamental constants, different configurations of quantum fields, different vacuum states. In most of these universes, conditions would be hostile to life. The vacuum might decay immediately, or the forces might be too strong or too weak to form atoms, or the expansion might be so rapid that matter never clumps into galaxies. But in a tiny fraction of universes, conditions would be just right. And naturally, we find ourselves in one of those rare, habitable universes. Not because we're special, but because we couldn't exist anywhere else. It's a kind of cosmic selection bias, like a lottery winner marveling at their good fortune while forgetting the millions who didn't win. This multiverse interpretation is controversial. It's not directly testable, and it strikes some physicists as a cop-out, a way of avoiding the hard work of explaining why our universe has the properties it does. But it does offer a framework for thinking about vacuum stability. If there are countless universes with different vacuum states, then somewhere in the multiverse, vacuum decay is happening right now. Entire universes are blinking out of existence, their false vacuums finally giving way to true vacuums, their laws of physics rewriting themselves into sterile simplicity. We just happen to be in one of the universes where it hasn't happened yet. And if the multiverse is infinite, then there are infinite copies of us, in infinite universes, all having this same conversation, all wondering if their universe will be the next to go. Now let's consider what happens at the boundary, the bubble wall itself. This is where the physics becomes truly exotic. The wall separating false vacuum from true vacuum isn't a physical object in the usual sense. It's a region of space where the Higgs field is transitioning from one value to another, a gradient in the fabric of reality itself. The thickness of this wall is determined by the strength of the Higgs field's self-interaction and the height of the energy barrier between the two vacuum states. Calculations suggest the wall might be incredibly thin, perhaps just 10 to the power of -15 meters across, about the size of a proton. But despite its thinness, the wall carries enormous energy. As it expands at light speed, it sweeps up the energy difference between the false and true vacuums, concentrating it into a moving shell of pure destruction. What would it be like to encounter such a wall? The question is almost meaningless, because _quote_11_ implies a duration, a moment of experience, and the wall moves at light speed. There would be no moment. One instant you'd be made of atoms governed by our current physics, and the next instant, if instant even applies, you'd be something else entirely, or more likely, nothing at all. The atoms in your body wouldn't have time to fly apart or rearrange. They'd simply cease to be atoms in any recognizable sense. The electrons would have different masses, the quarks would interact differently, the electromagnetic force binding molecules together would have a different strength. The entire concept of, quote, 13 would become undefined, like trying to run software written for one operating system on a computer that's just switched to a completely incompatible system. But here's a strange thought experiment proposed by physicist Don Page. What if you could somehow observe the bubble wall from a safe distance? What would you see? The answer depends on the energy difference between the vacuums. If the true vacuum has much lower energy than the false vacuum, the transition would release enormous amounts of energy, possibly creating a blast wave of radiation and particles. You might see a sphere of intense light, expanding outward, with the bubble wall itself invisible, but marked by the destruction it leaves in its wake. Stars would wink out as the wall passed through them, their fusion reactions suddenly impossible under the new physics. Galaxies would dissolve, their spiral arms unwinding as gravity itself changed strength. And then the wall would reach you, and your observation would end, not with a bang, but with a rewrite. Alternatively, if the energy difference is small, the transition might be quieter. The bubble wall might pass through space almost gently, leaving behind a universe that looks superficially similar but operates on fundamentally different rules. This scenario is even more unsettling because it raises the possibility that vacuum decay could have already happened, somewhere in the distant past, and we might be living in the aftermath without knowing it. Maybe the universe we observe, with its particular values of fundamental constants, is already a true vacuum state, and the quote, 14 we worry about is actually a theoretical construct that never existed. Or maybe we're in a cascade of vacuum states, each one metastable, each one eventually decaying into something lower, like a ball rolling down a staircase of energy levels, and we just happen to be on one of the middle steps. This brings us to the observational evidence, or rather, the lack of it. If vacuum decay were common in the universe, we might expect to see signs of it. We might observe regions of space where the laws of physics appear different, or expanding spheres of darkness where galaxies have been erased. We might detect gravitational waves from the violent expansion of bubble walls, or anomalies in the cosmic microwave background radiation left over from the Big Bang. But we see none of these things. The universe appears remarkably uniform, with the same physical laws applying everywhere we look, from the nearest stars to the most distant galaxies visible at the edge of the observable universe. This uniformity is itself a kind of evidence, not proof that vacuum decay is impossible, but a strong suggestion that it's at least rare enough that we haven't witnessed it in the 13.8 billion years of cosmic history we can observe. Yet, absence of evidence is not evidence of absence. The universe is vast, and our observations cover only a tiny fraction of space and time. A vacuum decay bubble could have formed a billion light-years away, and we wouldn't see it for a billion years. Or it could have formed in a region of space that's now beyond our cosmic horizon, carried away by the expansion of the universe faster than light can travel. The observable universe is like a small island in an infinite ocean. We can see the waves lapping at our shores, but we have no idea what storms might be raging beyond the horizon. Some physicists have proposed using the cosmic microwave background, the afterglow of the Big Bang, as a probe for vacuum stability. This radiation, which fills all of space and has been traveling toward us for over 13 billion years, carries information about the state of the universe when it was just 380,000 years old. If the vacuum were highly unstable, we might expect to see imprints of vacuum decay events in the early universe. Regions where bubbles formed and collapsed, leaving behind temperature fluctuations or polarization patterns in the microwave background. So far, observations from satellites like WMAP and Planck have found nothing unusual. The microwave background is smooth and uniform to an extraordinary degree, suggesting that the vacuum has been stable throughout cosmic history. But again, this is only evidence of stability in the observable universe, in the particular epoch we can see. It tells us nothing about what might be happening beyond our horizon, or what might happen in the future. There's also a philosophical dimension to vacuum decay that's worth exploring. Most existential threats, asteroid impacts, nuclear war, climate change, even the eventual heat death of the universe, are threats that exist within the framework of physical law. They're events that happen according to the rules, catastrophic but comprehensible. Vacuum decay is different. It's a threat to the rules themselves. It's the universe admitting that the laws we thought were eternal and unchanging are actually contingent, temporary, subject to revision without notice. This challenges our deepest intuitions about the nature of reality. We want to believe that there's a bedrock, a foundation, something we can count on. But quantum field theory suggests that even the foundation is floating, suspended over an abyss of possibility, held up by nothing more than probability and the fact that it hasn't fallen yet. This realization can be terrifying, but it can also be strangely liberating. If the universe could end at any moment through no fault of our own, through no action we could possibly take or prevent, then we're freed from a certain kind of cosmic responsibility. We didn't break the universe. We can't fix it. We're just here, riding the wave of an improbable stability, making the most of whatever time the false vacuum decides to give us. Every moment becomes a gift, not because we've earned it, but because it's another moment that the quantum dice have rolled in our favor. Every sunrise, every breath, every thought is a small miracle of cosmic patience. And yet, we continue to build, to plan, to dream about the future. We launch telescopes to study distant galaxies, knowing that the light we're seeing left those galaxies billions of years ago, when the universe was younger and perhaps more stable. We construct particle accelerators to probe the fundamental forces, measuring the masses of quarks and bosons with ever greater precision, refining our calculations of vacuum stability. We write equations on blackboards, trying to understand whether we're living in a false vacuum or a true one, whether the universe is stable or metastable or utterly precarious. And in doing so, we're engaging in an act of profound defiance, not against the universe, but against the uncertainty it imposes on us. We're saying that even if existence is contingent, even if reality could rewrite itself at any moment, we're going to try to understand it anyway. We're going to measure it, calculate it, describe it with mathematics, and test it with experiments. We're going to act as if the future exists, as if our actions matter, as if the universe is stable enough to reward our curiosity. Because here's the thing, it has been stable. For 13.8 billion years, through the formation of the first atoms, the ignition of the first stars, the assembly of galaxies, the formation of planets, the emergence of life, the evolution of consciousness. Through all of that, the vacuum has held. The Higgs field has maintained its value. The laws of physics have remained constant. The universe has declined, again and again, quadrillions upon quadrillions of times per second, in every cubic meter of space, to exercise its option to delete everything. And that track record, while it offers no guarantee about the future, is at least suggestive. Maybe the vacuum is more stable than our calculations indicate. Maybe there are protective mechanisms we haven't discovered yet. Or maybe we're just lucky, living in a rare epoch of a rare universe where the dice keep coming up in our favor. The physicist Max Tegmark has argued that we should think of vacuum stability not as a binary question, stable or unstable, but as a spectrum. At one end are universes where the vacuum is absolutely stable, where no amount of energy or time could ever trigger a transition. At the other end are universes where the vacuum is so unstable that it decays almost immediately after the Big Bang, never giving structure a chance to form. And in between are universes like ours, where the vacuum is metastable, stable enough to last for billions or trillions of years, but not stable enough to last forever. If this picture is correct, then vacuum decay isn't a question of if, but when. The universe has an expiration date, written into the quantum properties of the Higgs field, and we're living in the long, slow countdown to that final moment. But quote 1.5 might be so far in the future that it's effectively never. 10 to the power of 100 years is not just a long time, it's a timescale that defies human comprehension. By the time the vacuum is expected to decay, the universe will be unrecognizable. All the stars will have burned out. All the black holes will have evaporated. The temperature of space will have dropped to within a trillionth of a degree above absolute zero. The universe will be dark, cold, and empty, with nothing left but the faint whisper of quantum fluctuations in the void. And then, in that ultimate emptiness, a bubble of true vacuum might finally form, rewriting the laws of physics in a universe where there's nothing left to be affected by the change. It would be the ultimate anticlimax, the end of everything, happening in a cosmos where everything has already ended. Unless, of course, it happens sooner. Unless the calculations are wrong, or the measurements are off, or there's some factor we haven't accounted for. Unless a cosmic ray with just the right energy hits just the right spot in space, triggering a cascade that our equations said was impossible. Unless the universe surprises us, as it has so many times before. That's the nature of living in a quantum universe. Nothing is certain, everything is probabilistic, and the only thing we can count on is that we can't count on anything. So what do we do with this knowledge? How do we live in a universe that might delete itself in the next second? The answer, perhaps, is that we live exactly as we always have, with hope, with curiosity, with the stubborn insistence that our lives matter even if the cosmos is indifferent to our existence. We continue to ask questions, to seek answers, to push the boundaries of our understanding. We build civilizations, create art, love each other, dream about the future. Not because we're guaranteed a future, but because the act of building and creating and loving is itself meaningful, regardless of how long it lasts. And maybe, in some strange way, the precariousness of existence makes it more precious. If the universe were guaranteed to last forever, if the laws of physics were absolutely stable and unchanging, would we appreciate each moment as much? Would we feel the same urgency to understand, to explore, to make our mark on the cosmos before our time runs out. The possibility of vacuum decay, remote as it is, reminds us that existence is not a given. It's a gift, a temporary arrangement of quantum fields that happens to permit the existence of atoms, molecules, stars, planets, and conscious beings who can contemplate their own existence. And for now, in this moment, the gift continues. The vacuum holds. The universe persists. And we're here to witness it. There's a moment in the history of physics that doesn't appear in textbooks, but every theorist who studies vacuum stability knows the story. It happened in 2008, in the weeks before the Large Hadron Collider was scheduled to power up for the first time. A group of concerned citizens filed a lawsuit in federal court, arguing that the collider might create a black hole that would devour the Earth, or trigger a vacuum decay event that would destroy the universe. The lawsuit was dismissed. Physicists demonstrated conclusively that cosmic rays had been conducting the same experiments naturally for billions of years without incident. But in the quiet moments after the courtroom drama ended, some of the scientists involved admitted to each other that they'd done the calculations. They'd checked the numbers. They'd asked themselves the question that keeps vacuum theorists awake at night. What if we're wrong about how stable the vacuum really is? What if there's an energy threshold we haven't considered, a configuration of particles we haven't imagined, that could tip the Higgs field over the edge? The answer they found was simultaneously reassuring and deeply unsettling. The reassuring part, the energies achievable in particle accelerators, even the most powerful ones we can build, are nowhere near sufficient to trigger vacuum decay if the vacuum is even remotely stable. The unsettling part, the very fact that we can ask this question, that we can calculate the conditions under which reality itself might unravel, means we're living in a universe where the foundations are not as solid as we once believed. We're not standing on bedrock, we're standing on a frozen lake, and we're trying to determine how thick the ice is by drilling holes in it. Let's talk about what happens at the quantum level when a vacuum decay bubble forms, because the details reveal something profound about the nature of reality itself. In quantum field theory, the vacuum isn't a static thing. It's a seething foam of virtual particles, constantly appearing and disappearing, borrowing energy from the uncertainty principle and paying it back before the universe notices. These fluctuations are real. They create measurable forces, shift energy levels in atoms, and contribute to the mass of particles. Now imagine that in this quantum foam, a fluctuation occurs that's just a bit larger than usual. The Higgs field, instead of fluctuating around its normal value, briefly spikes to a much higher value, or drops to a much lower one. Most of the time, this fluctuation collapses back to the false vacuum state. The energy barrier is too high, the probability too low, and the universe snaps back to its familiar configuration. But quantum mechanics allows for tunneling. There's a non-zero probability that the Higgs field, instead of climbing over the energy barrier, simply appears on the other side of it, in the true vacuum state. When this happens in a small region of space, perhaps a volume no larger than a proton, you have the seed of a vacuum decay bubble. At this point, the physics becomes a race between two competing effects. On one side, the bubble wants to collapse back to the false vacuum because the surface tension of the bubble wall costs energy. On the other side, the bubble wants to expand because the interior is at lower energy than the exterior, and systems naturally evolve toward lower energy states. There's a critical size, calculated by Coleman and DeLucia, below which bubbles collapse, and above which they expand unstoppably. If a quantum fluctuation creates a bubble larger than this critical size, roughly 10 to the power of -26 meters, far smaller than an atomic nucleus, then the universe has crossed a point of no return. The bubble begins to expand. At first, the expansion is slow, limited by the energy available in the quantum fluctuation. But as the bubble grows, it releases more and more energy from the difference between the false and true vacuum states. This energy drives the expansion faster and faster until the bubble wall reaches the speed of light. And here's where the physics becomes truly inexorable. Once the wall is moving at light speed, nothing can stop it. No force in the universe can push back against it because forces propagate at the speed of light or slower. The bubble wall is like a wave front of causality itself, rewriting the laws of physics as it goes, and everything in its path is simply erased and replaced with something new. Now let's consider what this means for the structure of space-time inside the bubble. General relativity tells us that energy and matter curve space-time, creating what we experience as gravity. The vacuum, despite being the lowest energy state of quantum fields, still has energy. This is the famous cosmological constant, the energy density of empty space itself. In our false vacuum, this energy density is small but positive, which is why the universe is expanding and accelerating. But in the true vacuum, the energy density would be different. Most calculations suggest it would be lower, possibly even negative. And a negative vacuum energy would create a very different kind of space-time geometry. Physicist Sidney Coleman explored this in a paper that has become legendary in the field. He showed that a bubble of true vacuum with negative energy density would not simply expand into the surrounding false vacuum, it would create its own space-time, disconnected from the parent universe. The interior of the bubble would be a separate universe, with its own Big Bang, its own expansion history, its own eventual fate. From the outside, the bubble would appear to be a black hole, a region of space-time cut off from the rest of the universe by an event horizon. But from the inside, it would be an entire cosmos, potentially infinite in extent, with completely different physical laws. The bubble wall, moving at light speed in the false vacuum, would be the moment of creation in the true vacuum. A Big Bang happening right now, somewhere in space, giving birth to a universe that will never know we existed. This raises a dizzying possibility. Maybe our universe is itself the interior of a vacuum decay bubble. Maybe 13.8 billion years ago, in some parent universe with different physics, a quantum fluctuation created a bubble of lower energy vacuum, and that bubble is what we call the Big Bang. The expansion of our universe, the stretching of space that carries galaxies apart, might be nothing more than the ongoing expansion of a bubble wall in some higher dimensional space we can't perceive. We might be living inside a cosmic accident, a quantum fluctuation in a universe we'll never see, governed by laws we can't imagine. And if that's true, then our universe might itself spawn daughter universes through vacuum decay, creating an infinite fractal tree of bubble universes, each with its own physics, each unaware of the others, each thinking it's the only reality that exists. But let's return to our universe, our vacuum, our precarious existence. The question that haunts physicists is not just whether vacuum decay is possible, but whether we can predict when it might happen. And here we encounter one of the deepest problems in quantum mechanics, the measurement problem. In quantum theory, systems exist in superpositions of multiple states until they're measured or observed. Schrödinger's cat is both alive and dead until you open the box. An electron is in multiple places at once until you detect it. This isn't just a limitation of our knowledge, it's a fundamental feature of reality. The universe, at the quantum level, doesn't have definite properties until something forces it to choose. Now apply this to vacuum decay. Is the Higgs field in a definite state right now, or is it in a quantum superposition of false vacuum and true vacuum? If it's in a superposition, then in some sense, vacuum decay is both happening and not happening simultaneously, and it won't become definite until something, perhaps the expansion of a bubble to macroscopic size, forces the universe to choose. This interpretation, favored by some quantum cosmologists, suggests that vacuum decay is not an event that will happen at a specific time in the future, but rather a branching of reality into multiple timelines. In some branches, the vacuum decays tomorrow. In others, it lasts for 10 to the power of 100 years. And we, as observers embedded in this quantum universe, will only ever experience the branches where we continue to exist, at least until the moment when the bubble wall arrives and our branch terminates. This is a version of the anthropic principle taken to its logical extreme. We can only observe a universe where the vacuum hasn't decayed yet, not because we're special or protected, but because in all the branches where it has decayed, there's no one left to observe anything. It's a kind of quantum immortality, except instead of individual consciousness persisting across branches, it's the entire observable universe that persists in our experience, simply because we can't experience the branches where it doesn't. The universe might be ending and restarting constantly in countless branches of the quantum wave function, but we're trapped in the subset of branches where it hasn't happened yet, and will remain trapped there until the moment when all branches converge on vacuum decay, and there's nowhere left for consciousness to hide. Let's examine the experimental evidence more closely, because this is where theory meets reality in the most concrete way. The stability of the vacuum depends critically on the precise values of several fundamental parameters: the mass of the Higgs boson, the mass of the top quark, and the strength of the strong nuclear force. These aren't arbitrary numbers. They're measured quantities, determined by painstaking experiments at particle accelerators around the world. In 2012, when the Higgs boson was discovered at the Large Hadron Collider, its mass was measured at approximately 125.1 billion electron volts, with an uncertainty of about plus or minus 0.2 billion electron volts. That uncertainty might seem small, but it's crucial. If the true mass is at the lower end of the range, the vacuum is more stable. If it's at the higher end, the vacuum is less stable. We're literally 1 or 2 decimal places away from knowing whether the universe is fundamentally stable or living on borrowed time. The top quark mass is equally critical. Measured at about 173 billion electron volts, it's the heaviest known fundamental particle, and it plays a special role in vacuum stability because it couples very strongly to the Higgs field. The top quark's mass affects the shape of the Higgs potential energy curve at high energies, determining whether the curve has a second, deeper minimum at some enormous field value. Current measurements place us right on the boundary. The vacuum appears to be metastable, but just barely. A shift of 1% in the top quark mass, well within the current experimental uncertainty, could tip the calculation from metastable to stable, or from metastable to unstable. We're trying to determine the fate of the universe with measurements that have error bars. In 2015, a team of physicists led by Dario Buttazo published a comprehensive analysis combining all available data on the Higgs mass, top quark mass, and strong force coupling. Their conclusion? The vacuum is metastable with high confidence, but the lifetime is extraordinarily long, much longer than 10 to the power of 100 years. They calculated that the probability of vacuum decay occurring anywhere in the observable universe within the next billion years is less than 10 to the power of negative 100. For comparison, the probability of every atom in your body simultaneously quantum tunneling 1 meter to the left is vastly higher. This should be reassuring. And yet, the paper ends with a caveat that sends chills down the spine of anyone who reads it carefully. Quote, 16. New physics. This is the great unknown, the dragon lurking beyond the edge of the map. The standard model of particle physics is the most successful scientific theory ever devised, tested to extraordinary precision in thousands of experiments. But we know it's incomplete. It doesn't include gravity. It doesn't explain dark matter or dark energy. It doesn't account for the matter-antimatter asymmetry in the universe. There must be physics beyond the standard model, new particles and forces we haven't discovered yet. And any of these new phenomena could affect vacuum stability in ways we can't predict. Maybe there's a new particle that couples to the Higgs field, stabilizing the vacuum and ensuring it will never decay. Or maybe there's a new interaction that makes the vacuum even less stable than we think, reducing the expected lifetime from 10 to the power of 100 years to 10 to the power of 10 years, within the current age of the universe. Some physicists have speculated about what these new stabilizing mechanisms might be. One possibility is supersymmetry, a theoretical framework that predicts a partner particle for every known particle. If supersymmetry exists at the right energy scale, the partner of the top quark, called the stop squark, could modify the Higgs potential in just the right way to stabilize the vacuum completely. But searches for supersymmetric particles at the Large Hadron Collider have come up empty so far. If supersymmetry exists, it's either at higher energies than we can currently probe, or it doesn't affect vacuum stability in the way we hoped. Another possibility is extra dimensions of space, curled up at tiny scales, which could modify the behavior of the Higgs field at high energies. Or there could be multiple Higgs fields, interacting with each other in complex ways that stabilize the vacuum through mechanisms we haven't imagined yet. But there's also the opposite possibility. New physics could make things worse. In 2019, a team of cosmologists pointed out that the early universe, during the period of cosmic inflation, might have created conditions favorable for vacuum decay. Inflation is the theory that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang, smoothing out irregularities and setting the stage for the formation of galaxies. But inflation involves quantum fluctuations on enormous scales, and these fluctuations could have pushed the Higgs field to very high values in some regions of space. If the Higgs potential has the shape we think it does, with a second minimum at high field values, then these inflationary fluctuations might have triggered vacuum decay in the early universe. The fact that we're here suggests this didn't happen, or at least, it didn't happen in our region of space. But it raises the unsettling possibility that vacuum decay bubbles might have formed during inflation, and they could be expanding toward us right now, hidden beyond our cosmic horizon. Let's talk about what we could potentially observe if a vacuum decay bubble were approaching. This is where theoretical physics meets observational astronomy in fascinating ways. The bubble wall itself moves at light speed, so we'd never see it coming directly. But the interior of the bubble, with its different physics, might emit radiation or gravitational waves that travel ahead of the wall. If the true vacuum has a different value of the cosmological constant, the expansion rate inside the bubble would be different from outside, and this could create gravitational wave signatures detectable by instruments like LIGO or the planned LISA space-based detector. We might see a pattern of gravitational waves emanating from a point in space, growing stronger over time, indicating an expanding region of altered spacetime approaching at light speed. Alternatively, if the bubble formed in a region containing galaxies, we might observe those galaxies behaving strangely as the bubble wall passed through them. Stars might suddenly brighten or dim as the nuclear fusion reactions in their cores changed efficiency under new physical laws. Supernovae might occur with unusual frequencies or energies. The cosmic microwave background radiation passing through the bubble interior might be redshifted or blueshifted in unexpected ways. Astronomers have looked for such anomalies in the data from surveys like the Sloan Digital Sky Survey and the Dark Energy Survey, searching for any hint of a region where physics appears different. So far, they've found nothing. The universe looks the same in all directions, out to the limits of our observations. But absence of evidence is not evidence of absence, and the universe is vast beyond our ability to fully survey it. There's also a more subtle observational signature we could look for: the effects of vacuum decay on the cosmic microwave background itself. This radiation, released when the universe was just 380,000 years old, has been traveling through space for over 13 billion years. If a vacuum decay bubble had formed anywhere along its path, the radiation passing through the bubble would be affected. The photons might be absorbed, scattered, or shifted in frequency. We might see a circular pattern in the microwave background, a disk of altered temperature or polarization, marking the intersection of our past light cone with a bubble of true vacuum. Cosmologists have searched for such patterns in the data from the Planck satellite, which mapped the microwave background with unprecedented precision. They found no evidence of vacuum decay bubbles, which allows them to place limits on how common such events could be. If vacuum decay were happening frequently in the universe, we'd see the signatures. The fact that we don't suggests either that the vacuum is more stable than we fear, or that we're living in a particularly quiet region of the cosmos. But here's a thought that should give us pause. What if vacuum decay has already happened and we're living in the aftermath? What if the Big Bang itself was a vacuum decay event, a transition from some higher energy false vacuum to our current state. This idea, proposed by physicists including Alan Guth and Andre Linde, suggests that our universe might be a bubble of true vacuum that formed in a parent universe with completely different physics. The expansion we observe, the stretching of space that carries galaxies apart, might be the ongoing expansion of that bubble wall. And if that's the case, then the question isn't whether vacuum decay will happen in our future, it's whether it will happen again, creating a bubble within our bubble, a new universe, with new physics emerging from the quantum foam of our vacuum. This brings us to the concept of eternal inflation, one of the most mind-bending ideas in modern cosmology. The theory suggests that inflation, the exponential expansion that occurred in the early universe, never truly ends. It continues forever in some regions of space, while in other regions it stops, creating bubble universes like ours. Each bubble has its own Big Bang, its own expansion history, its own physical laws determined by how the fields settled into their vacuum states. And within each bubble, new bubbles can form through vacuum decay or other phase transitions, creating an infinite fractal structure of nested universes. We're not just living in a multiverse. We're living in a multiverse that's constantly giving birth to new multiverses, an endless proliferation of realities, each one a temporary island of stability in an ocean of quantum chaos. If this picture is correct, then vacuum decay isn't an existential threat. It's a creative force, the mechanism by which the multiverse explores the space of possible physical laws. Every vacuum decay event is an experiment, testing whether a new configuration of fields can support structure, complexity, life. Most experiments fail. Most bubbles create sterile universes where nothing interesting happens. But occasionally, by pure chance, a bubble forms with just the right properties. Forces balanced just so, particles with just the right masses, a cosmological constant small enough to allow galaxies to form, but large enough to prevent immediate collapse. And in those rare bubbles, given enough time, matter organizes itself into stars, planets, and eventually conscious beings who can look up at the sky and wonder why the universe is the way it is. We might be the result of countless failed experiments, countless bubbles that formed and collapsed or expanded into emptiness. We might be living in one of the infinitesimally rare bubbles where everything went right, where the vacuum was stable enough and the forces were balanced enough and the initial conditions were smooth enough to permit the emergence of complexity. And if that's true, then the fact that we exist at all is evidence that vacuum decay, far from being a threat, is the very process that made us possible. We're not despite vacuum decay, we're because of it. We're the universe's way of exploring what's possible when the quantum dice roll in just the right way. But this cosmic perspective, while intellectually satisfying, doesn't change the immediate question. Is our vacuum stable? Will it last long enough for us to fulfill whatever potential we have as a species, as a civilization, as conscious beings trying to understand our place in the cosmos? The honest answer is that we don't know. We can calculate probabilities, estimate lifetimes, place bounds on the parameters, but we can't eliminate the uncertainty. We can't prove that tomorrow won't be the day when a quantum fluctuation, somewhere in the vast expanse of space, creates a bubble of true vacuum that expands toward us at the speed of light. We can't guarantee that the universe will still be here in 1 billion years, or 1 million years, or even 100 years. All we can say is that it's been here for 13.8 billion years so far, and that's a pretty good track record. And maybe that's enough. Maybe the point isn't to achieve absolute certainty about the future, but to make the most of the present. To explore, to discover, to create, to love, to build civilizations and write symphonies and solve equations and raise children and plant gardens and dream about the stars. Not because we're guaranteed a future, but because the act of doing these things is meaningful in itself, regardless of how long it lasts. The universe might delete itself in the next second, or it might last for 10 to the power of 100 years. Either way, we're here now, in this moment, conscious and curious and alive. And that's not nothing, that's everything. I understand perfectly what you're thinking right now. You've read about quantum tunneling, false vacuums, bubble walls expanding at light speed, and somewhere in your mind, a voice is saying, "This sounds like science fiction. This sounds like the kind of speculation that belongs in a movie, not in a serious discussion about physics." And I want to acknowledge that voice, because it's not wrong to be skeptical. In fact, skepticism is exactly what science demands. So let's be absolutely clear about what we know, what we think we know, and what we're just guessing at. Here's what we know with certainty. The Higgs boson exists. We found it. On July 4th, 2012, physicists at CERN announced the discovery of a new particle with a mass of approximately 125 billion electron volts, and subsequent measurements confirmed it had all the properties predicted for the Higgs boson. This isn't speculation. This is experimental fact, confirmed by thousands of collision events, analyzed by independent teams, verified to a statistical significance that exceeds 5 sigma. That's the same level of certainty we have that smoking causes cancer, or that the Earth orbits the Sun. The Higgs field is real. It permeates all of space. It gives particles their mass. This is established physics. Here's what we think we know. The standard model of particle physics, which includes the Higgs field, appears to be mathematically consistent up to extraordinarily high energies. When physicists calculate how the Higgs field behaves at different energy scales, a process called running the coupling constants, they find that the equations remain well-behaved all the way up to energies approaching the Planck scale, about 10 to the power of 19 billion electron volts. This is remarkable. It suggests that the standard model might be valid across an enormous range of energies, from the everyday world up to the conditions that existed in the first fraction of a second after the Big Bang. But these calculations also reveal something unsettling. At very high energies, the Higgs potential appears to develop a second minimum, a lower energy state that our current vacuum could potentially decay into. This is where the false vacuum hypothesis comes from. It's not wild speculation, it's what the equations tell us when we extrapolate our experimentally verified theory to extreme conditions. And here's what we're guessing at. Whether that second minimum actually exists, whether quantum tunneling can actually create bubbles large enough to expand, whether the expansion of the universe suppresses or enhances the decay rate, whether new physics beyond the standard model stabilizes or destabilizes the vacuum, and most importantly, whether any of this will actually happen in the lifetime of the universe. These are educated guesses, based on solid mathematics and experimental data, but they're still guesses. The honest truth is that we're extrapolating our theories far beyond the regime where we've tested them, and extrapolation is always dangerous in science. History is littered with examples of theories that worked perfectly in one domain, but failed catastrophically when pushed into new territory. So why do physicists take vacuum decay seriously? Because the alternative is to assume that the patterns we've observed at low energies simply stop applying at high energies, that the mathematical structure of the standard model breaks down in some way we haven't discovered yet. And while that's certainly possible, even likely, given that we know the standard model is incomplete, it's not a scientific approach to simply wave our hands and say, quote, 18. Science proceeds by taking our best theories seriously, following their predictions wherever they lead, and then testing those predictions against reality. Vacuum decay is what you get when you take the standard model seriously and follow its mathematics to the logical conclusion. It might be wrong, but if it is wrong, we need to understand why, and that requires engaging with the theory on its own terms. Let me give you a sense of just how seriously the physics community takes this. In 2021, a team of researchers at the University of Southern Denmark published a paper in the journal Physical Review D, analyzing the stability of the Higgs vacuum using the most precise measurements available from the Large Hadron Collider. They didn't just calculate the expected lifetime, they calculated the uncertainty in that lifetime, accounting for all the experimental errors in the measurements of particle masses and coupling constants. Their conclusion? With 95% confidence, the vacuum lifetime is greater than 10 to the power of 95 years. That's a 1 followed by 95 zeros. For context, the current age of the universe is about 10 to the power of 10 years. The expected lifetime of the last stars is about 10 to the power of 14 years. The time for all black holes to evaporate is about 10 to the power of 100 years. So even at the lower bound of the confidence interval, the vacuum is expected to outlast everything else in the universe by an enormous margin. But here's what keeps physicists awake at night. That 95% confidence interval has a flip side. There's a 5% chance, 1 in 20, that the true vacuum lifetime is shorter than 10 to the power of 95 years, maybe much shorter. The calculations depend sensitively on parameters we haven't measured with perfect precision. A small shift in the Higgs mass, well within current experimental uncertainties, could reduce the vacuum lifetime by orders of magnitude. And while 10 to the power of 90 years is still an incomprehensibly long time, 10 to the power of 50 years starts to feel less comfortable. 10 to the power of 20 years is only a billion times the current age of the universe. 10 to the power of 15 years is within the lifetime of the longest-lived stars. The uncertainty isn't just academic. It spans a range that includes timescales we actually care about. Now let's talk about what would actually happen if vacuum decay occurred, because this is where the physics becomes simultaneously more concrete and more terrifying. Forget the abstract mathematics for a moment. Imagine you're an astronomer working at an observatory studying distant galaxies through a telescope. It's a normal night. You're taking spectra, measuring redshifts, cataloging the properties of stars billions of light years away. And then you notice something odd. One of the galaxies in your field of view, a spiral galaxy similar to the Milky Way, suddenly changes. The spectrum shifts. The emission lines from hydrogen and helium, which should be at specific wavelengths determined by the quantum mechanics of atoms, are at the wrong wavelengths. Not by a little, by a lot. As if the fundamental constants of nature had changed. You check your instruments. Everything is working correctly. You point the telescope at another galaxy. Normal spectrum. You point it back at the first galaxy. Still wrong. And then you notice that the anomaly is spreading. Galaxies near the first one are starting to show the same spectral shifts. And the region of affected galaxies is growing, expanding outward in a perfect sphere centered on that first galaxy. You calculate the expansion rate. It's exactly the speed of light. And in that moment, you realize what you're seeing. A vacuum decay bubble, expanding toward you, rewriting the laws of physics as it goes. You calculate how long until it reaches Earth. Maybe 1,000,000 years. Maybe 10,000. Maybe less. What do? Do you publish your findings, triggering worldwide panic? Do you keep quiet, hoping you've made a mistake? Do you spend your remaining time trying to understand the new physics inside the bubble, hoping to find some way to survive the transition? The answer, almost certainly, is that there's nothing you can do. The bubble is expanding at light speed. You can't outrun it. You can't shield yourself from it. You can't negotiate with it or deflect it or slow it down. All you can do is watch it approach, knowing that when it arrives, everything you know about physics will cease to apply. The atoms in your body will be governed by new rules. The chemical bonds holding your molecules together will have different strengths. The nuclear forces binding protons and neutrons in atomic nuclei will operate differently. You won't die in any conventional sense. You'll simply cease to be a coherent structure under the new physics. Your atoms will still exist, but they won't be your atoms anymore. They'll be something else, something that the new physics permits, and that something almost certainly won't include consciousness or life or anything resembling the complexity we associate with existence. This scenario isn't science fiction. It's a straightforward consequence of the mathematics of vacuum decay, applied to a universe where we have observational capabilities. And while the probability of it happening in our lifetime, or in the lifetime of our species, or even in the lifetime of our galaxy, is extraordinarily low, it's not zero. That's what makes this different from other existential risks. An asteroid impact is preventable in principle. We can detect asteroids, calculate their orbits, and potentially deflect them. Climate change is addressable. We can reduce emissions, develop new technologies, adapt to changing conditions. Even the heat death of the universe, trillions of years in the future, might be survivable for a sufficiently advanced civilization that can harvest energy from black holes or tap into the quantum vacuum. But vacuum decay is different. It's not a problem to be solved. It's a fundamental property of the universe we inhabit, a consequence of the quantum fields that make reality possible. If it happens, it happens, and there's nothing anyone can do about it. So let's confront the question directly. Should we be worried? Should you, as an individual human being living your life on Earth in the 21st century, spend any mental energy at all thinking about vacuum decay? The rational answer is no. The probability is so low and the timescale so long that it doesn't make sense to factor it into your decision-making. You're vastly more likely to die in a car accident, or from heart disease, or from any of 1,000 other mundane causes than to be affected by vacuum decay. If you're going to worry about existential risks, worry about nuclear war, or engineered pandemics, or artificial intelligence gone wrong, threats that are both more probable and more imminent. But there's another way to think about this question, one that's less about personal risk and more about the nature of existence itself. Vacuum decay forces us to confront the fact that the universe we inhabit is not a static, eternal backdrop for our lives. It's a dynamic, evolving system, governed by quantum fields that are themselves subject to change. The laws of physics that we treat as absolute and unchanging are actually contingent. They depend on the particular configuration of fields that happens to exist in our region of space and time. And that configuration, while stable for now, might not be stable forever. The universe is not a stage on which the drama of existence plays out. It's a participant in the drama, with its own agency, its own evolution, its own eventual fate. This realization can be unsettling, but it can also be liberating. If the universe is fundamentally impermanent, if even the laws of physics are temporary arrangements that could change at any moment, then nothing we do has cosmic permanence. But that doesn't make our actions meaningless. It makes them precious. Every moment of consciousness, every act of creation, every connection between minds, these things matter not because they'll last forever, but because they exist at all. In a universe that could delete itself at any second, the fact that we're here, thinking and feeling and wondering about our place in the cosmos, is a kind of miracle. Not a supernatural miracle, but a statistical one. The improbable persistence of complexity in a universe that's constantly testing whether it wants to continue existing. Let me share something that doesn't appear in the scientific papers, but that every physicist who works on vacuum stability knows. There's a psychological weight to this knowledge. When you spend your days calculating decay rates and tunneling probabilities, when you stare at equations that describe the end of everything, it changes how you see the world. Some physicists find it depressing. The idea that all of human civilization, all of art and music and literature and science could be erased in an instant by a quantum fluctuation we can't predict or prevent. But others find it strangely comforting. If the universe could end at any moment, then every moment we have is borrowed time, a gift we didn't earn and don't deserve. And that makes each moment more valuable, not less. There's a famous thought experiment in philosophy called the doomsday argument, which tries to estimate how long humanity will survive based on our position in the sequence of all humans who will ever live. The argument is controversial and probably flawed, but it raises an interesting question. How should we live if we knew the world would end soon? Should we abandon long-term projects and focus on immediate pleasures? Should we despair at the futility of our efforts? Or should we continue building, creating, exploring, loving, as if the future were guaranteed? Vacuum decay poses a similar question, except the timescale is cosmic rather than human, and the uncertainty is quantum rather than statistical. We don't know when or if it will happen. All we know is that it could happen, and that knowledge changes nothing and everything. Here's what I find most remarkable about the physics of vacuum decay. It's a prediction that emerges from our most successful scientific theory, tested and verified in thousands of experiments, and yet it describes an event that would invalidate all of our experiments, all of our theories, all of our knowledge. It's science predicting its own obsolescence. It's the universe telling us, through the language of mathematics, that everything we know is conditional, temporary, subject to revision without notice. And yet, we continue doing science anyway. We continue building particle accelerators, measuring constants to ever greater precision, refining our theories, pushing the boundaries of knowledge. Not because we think our knowledge will last forever, but because the pursuit of knowledge is valuable in itself, regardless of how long it endures. This is the paradox at the heart of vacuum decay. It's simultaneously the most abstract and the most concrete threat imaginable. Abstract because it involves quantum field theory, high-energy physics, mathematical extrapolations far beyond anything we can test directly. Concrete because if it happens, it's not a distant, impersonal catastrophe. It's the immediate, total erasure of everything you are and everything you know. There's no middle ground, no partial destruction, no survivors to tell the tale. Just a bubble wall, expanding at light speed, rewriting reality as it goes. And yet, here we are. The vacuum hasn't decayed. The Higgs field maintains its value. The laws of physics remain constant. Every second that passes is another second that the universe has chosen stability over chaos, persistence over annihilation. We're living in the longest-running experiment in cosmic history, an experiment to see how long a metastable vacuum can last. And so far, for 13.8 billion years, the answer has been long enough. Long enough for stars to form and planets to cool and life to emerge and consciousness to develop and civilizations to rise and fall and rise again. Long enough for beings like us to exist, to wonder, to calculate the probability of our own erasure, and to continue existing anyway. The physicist Frank Wilczek, who won the Nobel Prize for his work on the strong nuclear force, once wrote that the universe is a quote, 20 . Not a beautiful answer, a beautiful question. The question of why anything exists at all, why the laws of physics are what they are, why the universe is comprehensible to minds like ours. Vacuum decay adds another layer to that question. Why has the universe remained stable long enough for us to ask these questions? Is it just luck? A statistical fluctuation in an infinite multiverse? Is it a selection effect, where we can only exist in universes that haven't decayed yet? Or is there something deeper, some principle we haven't discovered, that ensures the vacuum is more stable than our calculations suggest? We don't know, and that's okay. Science isn't about having all the answers. It's about asking better questions, refining our understanding, accepting uncertainty while still pushing forward. Vacuum decay is the ultimate expression of that uncertainty. It's the universe reminding us that we don't have all the answers, that our knowledge is incomplete, that reality is stranger and more precarious than we ever imagined. And yet, we keep going. We keep building telescopes and accelerators, keep measuring and calculating, keep trying to understand the cosmos we inhabit. Not because we're guaranteed success, but because the alternative, giving up, accepting ignorance, living in fear of what we don't know, is worse than any quantum fluctuation could ever be. So here's where we stand, at the end of this exploration of vacuum decay. We live in a universe that might be fundamentally unstable, balanced on the edge between existence and oblivion, held together by nothing more than probability, and the fact that it hasn't collapsed yet. The laws of physics that govern our lives might be temporary, contingent, subject to change without warning. A bubble of true vacuum could be expanding toward us right now, and we'd never see it coming. And yet, none of this changes what we should do with our lives. We should still love, create, explore, build, dream. Not despite the uncertainty, but because of it. Because in a universe where nothing is guaranteed, where even the laws of nature are provisional, the fact that we exist at all is extraordinary. The fact that we can understand even a fraction of how the universe works is miraculous. And the fact that we continue to exist, second after second, year after year, eon after eon, is the greatest gift the cosmos could possibly give us. The vacuum holds. For now. And that's enough. There's a photograph that cosmologists sometimes show at the end of their lectures, though it never appears in the scientific papers. It's an image of Earth taken by the Voyager 1 spacecraft in 1990 from a distance of 6 billion kilometers, just beyond the orbit of Neptune at the very edge of the solar system. In that photograph, Earth appears as a single pixel, a pale blue dot suspended in a sunbeam, barely visible against the vastness of space. Carl Sagan, reflecting on that image, wrote that it shows our planet as what it truly is, a mote of dust, suspended in a sunbeam, the only home we've ever known. But here's what Sagan didn't say, what perhaps he couldn't say without undermining his message of cosmic humility. That pale blue dot, that single pixel of light, contains every human being who has ever lived, every thought that's ever been thought, every equation that's ever been written, including the equations that describe vacuum decay, including the calculations that suggest the universe itself might be as fragile as we are. Let's talk about what vacuum decay means for the biggest question in philosophy. Why is there something rather than nothing? This question has haunted thinkers for millennia, from ancient Greek philosophers to modern cosmologists. And vacuum decay offers a strange kind of answer, or rather, it reframes the question entirely. Because if our universe exists in a false vacuum state, then something and nothing aren't absolute categories. They're relative positions on a landscape of possible vacuum states. What we call something, the universe with its stars and galaxies and conscious beings, might be nothing more than a temporary fluctuation, a metastable configuration of quantum fields that happens to permit complexity. And what we call nothing, the true vacuum, the lowest energy state, might actually be something, just something so different from our current reality that we can't recognize it as existence at all. This connects to a deep idea in quantum cosmology called the quote 25, developed by Stephen Hawking and James Hartle in the 1980s. They suggested that the universe doesn't have a beginning in the conventional sense. No moment of creation, no first cause, no edge to space-time. Instead, time itself emerges from a quantum state where the distinction between space and time breaks down. In this framework, asking what came before the Big Bang is like asking what's north of the North Pole. The question doesn't make sense because before requires time, and time didn't exist yet. Now apply this thinking to vacuum decay. If a bubble of true vacuum forms and expands, creating a new universe with new physics, does that new universe have a beginning? Or does it emerge from a timeless quantum state, just like our universe might have? And if so, then vacuum decay isn't the end of existence. It's a transition between different modes of existence, different ways that quantum fields can configure themselves into something we might call a universe. But let's be honest about what this means for us, for conscious beings made of atoms that depend on the current configuration of the Higgs field. Even if vacuum decay creates a new universe, we won't be there to see it. Our atoms will be disassembled and reassembled according to new rules. Rules that almost certainly won't permit the existence of chemistry, biology, consciousness. From our perspective, vacuum decay is still the end. But from the universe's perspective, if we can even speak of the universe having a perspective, it might be a transformation, a metamorphosis, a shedding of one set of physical laws in favor of another. The universe doesn't die, it just becomes something else. This raises a question that sounds like science fiction, but is actually deeply philosophical. Could consciousness survive a vacuum decay transition? Not our consciousness, not biological minds dependent on neurons and synaptic connections, but some other form of information processing, some pattern of organization that could persist across the boundary between false vacuum and true vacuum. The answer, according to everything we know about physics, is almost certainly no. Consciousness, as we understand it, requires complexity, neurons firing in patterns, information being stored and retrieved, feedback loops creating the illusion of a unified self. And complexity requires energy gradients, stable structures, predictable physical laws. The true vacuum, with its different particle masses and force strengths, almost certainly couldn't support any of this. But quote 27 isn't the same as definitely. And in a universe governed by quantum mechanics, where particles can tunnel through barriers and cats can be simultaneously alive and dead, maybe, just maybe, there's a configuration of the true vacuum that permits some form of complexity we can't imagine, some substrate for consciousness so alien to our experience that we wouldn't recognize it as consciousness at all. The physicist Freeman Dyson once speculated about the far future of the universe, trillions upon trillions of years from now, when all the stars have died and all the black holes have evaporated. He suggested that consciousness might persist even then, embodied not in biological organisms, but in vast clouds of charged particles, thinking thoughts at an infinitely slow rate to conserve energy in a cooling cosmos. It's a beautiful idea, though probably wrong. The universe's accelerating expansion will likely tear apart even these tenuous structures long before they can think their first thought. But it illustrates a deeper point. Consciousness might not be tied to any particular substrate. It might be a pattern, an organization of information, that could, in principle, be implemented in many different physical systems. And if that's true, then maybe, just maybe, some form of consciousness could survive the transition to a true vacuum, encoded in whatever structures the new physics permits. But let's return to Earth, to the present moment, to the universe as we actually experience it. Because here's what vacuum decay really teaches us: the preciousness of the ordinary. Every breath you take requires the electromagnetic force to have exactly the strength it does, holding molecules together in your lungs. Every thought you think requires electrons to have exactly the mass they do, allowing them to flow through neural circuits at the right speed. Every heartbeat depends on the weak nuclear force operating at exactly the right strength to power the fusion reactions in the sun, which provides the energy that powers all life on Earth. The universe is a tower of dependencies, each layer resting on the layers below, all the way down to the quantum fields that define what matter and energy even are. And that tower is balanced on a knife edge, held together by the fact that the Higgs field happens to have the value it does. Think about what this means for the concept of natural law. We're used to thinking of physical laws as eternal, unchanging, written into the fabric of reality itself. Newton's laws, Maxwell's equations, Einstein's field equations, these aren't just descriptions of how things happen to behave. They're statements about how things must behave, always and everywhere. Except vacuum decay tells us this isn't quite true. Physical laws are contingent on the vacuum state. Change the vacuum and you change the laws. The speed of light might be different. The strength of gravity might be different. The very concept of _quote_29_ might be different. What we call laws of nature are really just local bylaws, rules that apply in our particular cosmic neighborhood, in our particular epoch, in our particular vacuum state. They're not eternal truths, they're temporary arrangements, subject to revision without notice. This should be terrifying, and yet there's something almost comforting about it. Because if the laws of physics are contingent, then so is everything that follows from them. The fact that you exist, that consciousness exists, that the universe is comprehensible to minds like ours, none of this was inevitable. It's all contingent on the Higgs field having the value it does, on the vacuum being stable enough for long enough, on a chain of improbable events stretching back 13.8 billion years to the Big Bang. You are not just improbable, you are impossible, except for the fact that you exist anyway. You are a violation of the expected, a statistical fluctuation that became conscious and started asking questions about its own existence. Let me tell you what we don't know, because this is where honesty demands we confront the limits of our understanding. We don't know if the vacuum is truly metastable, or if our calculations are missing something that makes it stable. We don't know if there's new physics beyond the standard model that changes everything. We don't know if the multiverse is real, or if we're living in the only universe that exists. We don't know if vacuum decay has already happened somewhere in the cosmos, with a bubble wall racing toward us at light speed. We don't know if consciousness could survive such a transition, or if the true vacuum could support any form of complexity at all. We don't know if the universe will last for 10 to the power of 100 years, or 10 to the power of 10 years, or 10 more seconds. We don't know, and we may never know, because some of these questions might be fundamentally unanswerable, protected by the cosmic horizon, or the uncertainty principle, or the simple fact that we can't run experiments on the entire universe. And you know what? That's okay. Science has never been about achieving perfect certainty. It's been about reducing uncertainty, refining our models, getting closer to the truth, even if we never quite reach it. Every measurement we make, every experiment we run, every calculation we perform, these narrow the range of possibilities, constrain the space of what could be true. We may never know the exact lifetime of the vacuum, but we know it's longer than the current age of the universe. We may never know if the multiverse exists, but we know our universe is at least possible because we're living in it. We may never know what the true vacuum would be like, but we know our false vacuum, if that's what it is, has been stable enough to permit the emergence of stars, planets, life, and minds capable of contemplating their own existence. There's a concept in Buddhism called impermanence, the idea that nothing lasts forever, that all things arise and pass away, that clinging to permanence is the root of suffering. Vacuum decay is the ultimate expression of impermanence, the recognition that even the universe itself is temporary, that even the laws of physics are subject to change. But Buddhism also teaches that recognizing impermanence isn't cause for despair, it's cause for appreciation. If nothing lasts forever, then every moment is unique, unrepeatable, precious. The flower is beautiful, not despite the fact that it will wilt, but because of it. The sunset is magnificent, not despite the fact that it will fade, but because it will fade. And existence itself is miraculous, not despite the fact that it could end at any moment, but because it could end at any moment, and yet it continues anyway. Remember how we started this journey? With you, watching this video, every atom in your body suspended in what might be a cosmic lie. We've traveled from that personal moment through quantum field theory, through particle physics and cosmology, through calculations of decay rates and bubble walls expanding at light speed, through multiverses and eternal inflation and the limits of human knowledge. And now we return to you, to this moment, to the fact that you're still here. The vacuum hasn't decayed. The Higgs field maintains its value. The laws of physics remain constant. You are still made of atoms, still conscious, still capable of wonder. What does it mean to live in a universe that could delete itself in the next second? It means that existence is not a given, it's a gift. Not a gift from some cosmic benefactor, but a gift from the quantum fields themselves, from the probability distributions that govern reality at its deepest level. Every second that passes is another second that the universe has chosen, if we can speak of the universe choosing, to continue existing in its current form. Every breath you take is a small miracle of cosmic stability, the Higgs field declining once again to tunnel through to the true vacuum. Every thought you think is evidence that the laws of physics are still the same as they were a moment ago, that the electromagnetic force still has the right strength, that electrons still have the right mass, that the tower of dependencies we call reality is still standing. And here's the beautiful thing. None of this requires you to do anything differently. You don't need to live in fear of vacuum decay. You don't need to change your plans or abandon your dreams or treat every moment as if it might be your last. Because the probability is so low and the timescale so long that vacuum decay is effectively irrelevant to your life. You're vastly more likely to die of causes that are mundane, preventable, and entirely within the framework of our current physics. The universe will almost certainly outlast you, and your children, and your children's children, and every generation of humans that will ever live. The vacuum will hold. The laws of physics will remain constant. The tower will stand. But knowing that it might not, knowing that there's a non-zero probability, however small, that reality itself could rewrite itself at any moment, that knowledge changes something subtle but profound. It reminds us that we're not entitled to existence. We're not owed a future. We're not guaranteed that the universe will continue to operate according to the rules we've discovered. We're here by accident, by chance, by a chain of improbable events that includes the vacuum remaining stable for 13.8 billion years. And that makes every moment we have more valuable, not less. It makes every discovery more meaningful, every connection more precious, every act of creation more significant. The physicist Richard Feynman once said that the universe is not only stranger than we imagine, it's stranger than we can imagine. Vacuum decay is proof of that strangeness. It's a prediction that emerges from our most successful scientific theory, and yet it describes an event so alien to our experience that we can barely comprehend it. A bubble of altered reality, expanding at light speed, rewriting the laws of physics as it goes. It sounds like fantasy. It sounds like the kind of thing that couldn't possibly be real. And yet, the mathematics is clear, the logic is sound, and the experimental evidence, the mass of the Higgs boson, the mass of the top quark, the behavior of quantum fields at high energies, all points in the same direction. The universe might be metastable, reality might be temporary, existence might be contingent. And you know what the strangest part is? We're okay with that. We've looked into the abyss of cosmic uncertainty, calculated the probability of our own erasure, confronted the possibility that everything we know could end without warning, and we've decided to keep going anyway. We keep building particle accelerators, keep measuring constants, keep refining our theories. We keep writing poetry and composing symphonies, and falling in love, and raising children, and planting gardens, and dreaming about the future. Not because we're guaranteed a future, but because the act of building and creating and loving is meaningful in itself, regardless of how long it lasts. This is what it means to be human in a universe governed by quantum mechanics. We live with uncertainty. We accept that we can't know everything, can't predict everything, can't control everything. We acknowledge that the universe is stranger and more precarious than we ever imagined. And then we get up in the morning and make breakfast, and go to work, and laugh with friends, and watch the sunset, and marvel at the fact that we're here at all, that consciousness exists, that the universe has organized itself in such a way that parts of it can contemplate the whole. Vacuum decay is the ultimate reminder that we're not separate from the universe, we're part of it. We're made of the same quantum fields that might decay at any moment. We're subject to the same laws of physics that might change without warning. We're participants in the same cosmic experiment that's been running for 13.8 billion years, testing whether a metastable vacuum can support the emergence of complexity, life, and consciousness. And so far, the answer has been yes. So far, the vacuum has held. So far, we're here. And maybe that's the real lesson of vacuum decay. Not that existence is fragile, though it is. Not that the universe is indifferent to our survival, though it is, but that we're here anyway. Despite the improbability, despite the uncertainty, despite the fact that the quantum fields could tunnel to a lower energy state at any moment and erase everything we are and everything we know, despite all of that, we exist. We think, we feel, we wonder. We calculate the probability of our own erasure, and then we go outside and look up at the stars and feel awe at the vastness of it all. The vacuum holds. For now. For this moment. For the 13.8 billion years that have passed, and the unknown number of years that remain. And in that holding, in that temporary stability, in that improbable persistence of the false vacuum, if that's what it is, we find not despair, but wonder. Not fear, but gratitude. Not meaninglessness, but meaning itself, created not by the universe, but by us, by conscious beings who can look at the equations describing their own potential annihilation and choose to find beauty in them anyway. You are made of atoms that shouldn't be stable. You are governed by laws that might be temporary. You exist in a universe that could rewrite itself at any second. And yet here you are, reading these words, thinking these thoughts, existing anyway. That's not a tragedy, that's a miracle. Not a supernatural miracle, but a quantum mechanical one. The improbable persistence of complexity in a universe that's constantly testing whether it wants to continue existing. The answer, so far, has been yes. The universe wants to continue. The vacuum wants to hold. Reality wants to persist. And we, as conscious parts of that reality, get to witness it. We get to measure it, calculate it, understand it. We get to write equations describing the end of everything, and then go home and hug our children and watch the stars and feel grateful for another day in a universe that could have ended but didn't. That's the gift of impermanence. That's the beauty of uncertainty. That's what it means to live in a universe that could delete itself in the next second, but chooses, again and again, moment after moment, to continue existing in